Okay, so I'm going to present today a basis for the cone of centrally symmetric generalized permutahedra, and this is joint work with my advisor Spencer Backman. And I will define all of these words except for basis probably. Hopefully you guys already know that one. So just a quick review, what is the Minkowski sum of polytopes? If I have two convex polytopes, the Minkowski sum is just pointwise addition for every single point in each of the polytopes. So for example, very basic two line segments in R2. The Minkowski sum ends up being this quadrilateral. You can see that P basically just got translated upwards by this direction, this vertex of Q, and got translated over by this vertex of Q, and then the convex whole of all those points gives the Minkowski sum. And the normal fan in this talk, we use the convention of the outer normal, which comes from maximizing this inner product that we saw last week with Thomas Lamb's talk. And for every facet of your polytope, you have your outer normal vector. So you can just denote it by the facet that you've labeled it. And then for every other face of your polytope, you're going to consider the facets that contain it. So for example, this vertex is a face of the polytope and it's contained by these facets. So the normal cone associated to that vertex will be the span of these two rays. So you get this entire cone corresponding to that vertex up top. And then the normal fan is a collection of all of these normal cones for your polytope. So okay, very special kind of polytope, the nth permutahedron, or it's actually not full dimensional, so often denoted pi subscript n-1. It's just the polytope. You take the convex whole of all vertices that are all permutations of the point 1, 2, up to n. Here is the two-dimensional permutahedron, which is actually the third permutahedron, and you can see that it's a hexagon sitting in 3 space. And if I take its normal fan, actually a very special name, when you have the normal fan of the permutahedron, it's called the braid arrangement. So what is a generalized permutahedra? Actually, I think it was Jacob mentioned them earlier in his talk. If I take a permutahedron and I deform it by shifting its vertices but maintaining all of its edge directions, I say that's a deformation of the permutahedron. So for example, if I take this facet and I pull it out, I've shifted those two vertices, but all the other directions have been maintained. And I obtain this polytope on the right. If I look at their two normal fans, I can see that the polytope on the right, which is the deformation, also coarsens, its normal fan coarsens the braid arrangement that we started with. So these are equivalent definitions, a deformation and a coarsening of the normal fan. And specifically, if you start with the permutahedron and you deform it, the polytope that you obtain is called a generalized permutahedron, or if you're a good savant, it is a deformed permutahedron. So here's a bunch of equivalent definitions for them. 2 and 3 we just saw. Number 4 is going to come in handy later, and it was also mentioned earlier in one of the talks. The edges of a generalized permutahedron are parallel to these line segments. And number 5 won't be used in this talk, but it's a very common definition that you often see in the literature, defining generalized permutahedron in terms of its submodular support function. So number 4 will come in handy soon. But first, what does it mean to be centrally symmetric? A polytope is centrally symmetric if you take its negative and it's the same thing as what you started with. And here's just an observation. This is a characterization of centrally symmetric polytopes. If I take the polytope and I take the Minkowski sum with its negative and I cut by this factor of 1/2, I actually get my original polytope. It's a fun little exercise. So I'm going to focus on centrally symmetric generalized permutahedra, CSGP. So anything that is a deformation of a permutahedron and it's centrally symmetric. Because I want to define something called the centrally symmetric deformation cone. So if I start with a fan that is centrally symmetric and projective, that just means that the polytope it corresponds to, it has rational vertices. The centrally symmetric deformation cone of this fan is defined as the space of all centrally symmetric polytopes whose normal fan coarsens the fan that I started with. We're going to apply it specifically to when F is the braid arrangement. So we know that the polytopes that coarsen the braid arrangement are generalized permutahedra, and we're going to also add this condition that they must be centrally symmetric. And as far as we can tell, this hasn't really been defined in the literature, the deformation cone for the braid arrangement. Other various projective fans are very well studied, but it doesn't seem that anyone has really looked at the centrally symmetric deformation cone of the braid arrangement. So very cool. Here's a proposition. don't worry about the words. Basically, it just very easily allows us to calculate the dimension of the space that we're looking at. So we have this cone of centrally symmetric generalized permutahedron. How big is it? What's the dimension? It has 2 to the n minus 2 rays, the braid arrangement does, and I can just cut that in half to obtain the dimension of the cone that I'm looking at. So 2 to the n minus 1 minus 1. So now that I have the space I want to explore, what is a basis for it? Well, Ardila, Carolina Benedetti, and Jeffrey Doker found a nice way to express just a generalized permutahedron in terms of assigned Minkowski sum of standard simplices. And if we combine this with this observation about centrally symmetric polytopes, we obtain a really nice set of polytopes that form a spanning set for the cone of centrally symmetric generalized permutahedra, and they are called root polytopes. Root polytopes have a couple definitions. This is the one that we're opting to use. You just take the convex whole of subsets of roots of type AN, and you can do a quick check that if I take a standard simplex and I add it to its negative, I do indeed get all of these root polytopes for various subsets S. So they span this space. Here's a nice example. If I take the tetrahedron and I add it to its negative, I get this like the root polytope, some people call it, for the lattice A3. And what's really cool about it is you can actually see here is the three-dimensional permutahedron. And if I take all the square faces and I squish them in, I obtain exactly this thing on the left. So it's a clear deformation, depending on how good your geometry is, but you can visualize it. Yeah, so we have that the root polytopes span this space. So how can I form a basis from this collection that I have? Well, we made an observation that the odd dimensional root polytopes for a given dimension n arise from exactly these even subsets of our ground set. You get cut down by one dimension when you take the convex whole of all of these appropriate vertices. And so famously, there are 2 to the n minus 1 even subsets of element of n sets of n elements. And then we ignore the anti-set because it doesn't produce a polytope that's useful. So in total, we have 2 to the n minus 1, which is exactly the dimension of the cone that we're working in. So in order to finish the proof, you would also need to show that this collection of odd-dimensional root polytopes are linearly independent, which we did. If you would like to read our paper that is not out yet. But officially, this gives us that the odd-dimensional root polytopes in a given dimension give a basis for the space of all centrally symmetric generalized permutahedron.
Sienna, do you have a question? Yeah, Matt.
What about the extremal rays of the cone?
Great question. What do they represent?
Yeah, how many are they?
How many are there? I don't know if I know that answer off the top of my head. No? Okay, that's reassuring.
Can you go back to your theorem slide?
Yes.
Time for maybe one more question. All right, Matt, let's thank Sienna.